Hello everybody. Today I thought we could talk about what transformers are. Not the movie, but the electrical type of transformer. So very few people, and I wouldn't say very few people, but not many people know what transformers are, and even fewer know how they work. So we're going to go over both of those today. Now, for the people who don't know what a transformer is a special type of inductor. It can be represented, it's usually represented in a schematic like this. As you can see, that's what we have. So, what transformers are used in everything from a microwave oven to phone chargers to electric car chargers to the power that goes into your house. They're everywhere, and they're fairly simple devices. I have some examples here of some transformers. So, we'll start with this. This is a wall adapter, as most people would recognize this. And so, yeah, this can power a lot of different things. Usually, it inputs AC, alternating current. All transformers only work with AC, so they must have an input of AC. And then some wall adapters have an output of AC, or like this one, as a DC output. So inside we have a rectifier, which converts AC to DC. We'll go over that in another video. Here are some more examples of what they would look like. This is called the toroidal transformer. So it has, underneath this plastic cover is a steel core, and then there's the two different windings. This is a high frequency switching transformer. So this is what you would find in a wall adapter. This one's specifically a very large one. Here's another one that's from a switching power supply. And these tiny guys, these are regular iron core transformers. These have a ferrite core, so they don't magnetize as well. I'll go over that in a little while. These two, they have steel laminated windings here. And so that's a metal steel laminated windings, and that's for magnetization, which we'll go over, as I said, later. And then this one's fairly easy to see. We have right here our primary input. So we have two sides, because it's a circuit, so you need two different sides. And then here we have our secondary, and we have four different outputs, probably because this has two separate windings in it. And then we have transformers like this. This is my Variac, and this is a variable transformer. This is a very special type of transformer. It's not a conventional type of transformer. It's called an auto transformer because it has only one winding. We'll go over how this exactly works in the next video. Getting back to what the transformers, how they work. Now we'll go over how they work. So, as you can see, we have primary and secondary. The primary winding is usually attached to, not always, but usually if you're going to plug it into an AC source, you're probably going to plug it into whatever comes out of the wall. In Europe, that's going to be 230 volts. Over here in North America, that's going to be 120 volts. Although we do have 240 volt transformers here in North America as well. The operation of a transformer basically steps up or steps down a voltage. So, for example, here's two different examples. This wall example, with this wall adapter, this would be stepping down because we're putting in 120 volts, and in this case, we're getting out 6 volts DC. So that would mean that so we'd be stepping down. A step up would be in a microwave oven, is a good example, because in a microwave oven, we have a one winding, the primary, we put in 120 volts, and on the secondary, we get about 2,000 volts, which is what we need to run the magnetron that cooks the food. So once we have that, so that's the basic premise. They just step up or step down a voltage. And usually when you step down a voltage, you get a raised current. So the current, you can usually draw more current. So in things like these transformers, this one isn't a very good example because it's equal. But things like this one, our primary is going to be very, very, very thin wire, and that's to make sure that we have enough impedance, first of all, for the we have enough impedance for the AC not to be shorted, and then also because it's an inductor, which is just a coil of wire, it also has inductance. So we have very, very thin wire, and so we can't draw much current out of that wire. On the secondary, we're going to have a little bit thicker wire. So that'll allow us to draw a little bit more current without it melting and catching fire and whatever else. So when we're trying to calculate how we can get how to wind a transformer, because like I said, it's a ton of windings around this core. We have what's called a winding ratio. So that is the primary windings. So in this case, I would say that probably for, let's go with 2,000 windings. You can't go with too small because, like I said, then you don't have enough impedance and inductance and you short the AC supply, which is not good. And then on the bottom is how many windings we want on our secondary. So let's say 1,000. So that's basically a 2-to-1 ratio. And well, let's go with another way to do this with voltage, because we can do this another way that will make more sense. But this would be a 2-to-1 ratio, right? If we say want to calculate for a transformer with different voltages, say we want 120 volts in the primary and 60 volts on the secondary. We can reduce this and we still have our 2-to-1 ratio, right? So if we have that 2-to-1 ratio, we still have our 2-to-1 ratio with this setup. So then we can multiply this 2-to-1 by whatever's appropriate for the windings. So however much impedance we do other calculations for impedance. I'm not going to go into that in this video, but we would do other calculations to calculate how much impedance we need in order to not short the supply. And then once we know how much impedance we need, we can kind of figure out how many windings we need, and then we can multiply that with our winding ratio. Now, this is the confusing part, is how transformers work. We know that when we put power into a conductor, power meaning voltage and current, voltage times current, I mean, that would mean when we put power into a transformer, we're going we know that when we put power into a conductor, we know that it will produce a magnetic field. The currents will produce a certain magnetic field. So That's how an inductor kind of stores energy in the form of a magnetic field. So if we have, and this is Faraday's law of electromagnetic induction, I'll write this down. Faraday's law of electromagnetic induction says, magnetic fields in one conductor can be picked up in another in the form of an induced voltage. So, magnetic fields in one conductor can be picked up in another in the form of an induced voltage. So, what that basically means, if we're putting in we're putting in 120 volts into our primary, and we want, if we're putting in 120 volts into our primary, and it's wound around, and it's an inductor, so it has a magnetic field. And then, to strengthen this magnetic field, we know that steel, or iron, is ferromagnetic, meaning that, ferromagnetic, meaning that it's, it can be magnetized and demagnetized. So magnets will react with it. So we have this iron core here, which can be, it helps to, because we still get our magnetic fields out of the inductor no matter what. But the iron core helps to strengthen those magnetic fields and help the secondary pick it up a little bit better. Because without that, especially with how much current, the more current we put in, the stronger the magnetic field is going to get. But since this transformer, especially with how small this one is, we would not be able to draw very much power at all. We would not be able to put very much power into it at all. So, because of that, we have to, the secondary is not going to pick up that very well. So, the iron core helps to strengthen it. So, if we're going to draw this scenario, we can draw it like this. So, I'll redraw our transformer diagram here. Okay, now, let's say we're going to apply our AC source, and this is 120 volts, 120 VAC, volts AC. So, now, this is going to create a magnetic field. And this magnetic field is going to go around we can look at this with the right hand rule. So my thumb is the direction of current in the wire. So if so that's the direction of current in the wire. And then wherever all my other fingers are going, that's the direction of the magnetic field. So, or I'll try to link this video, but the Electroboom did a really good job of explaining this. Then there's this right-hand rule, which the middle finger is for magnetic field or B field. The index finger is for current, and then the thumb is force. So the thumb would be force. So if our this one's going to make more sense for this. So if the current is going this way and our magnetic field is going around that way, and this is set up we'll look at it like this, because our current is going to be flowing around and around and around like this. And then our magnetic fields are going to go around like this. So we will then have magnetic fields. I'm not drawing this very well, but bear with me. That's going to go around that magnetic core, which will help magnetize that. And then it goes around our other winding, which magnetizes that. And that's how we're able to convert that voltage. Now, I'm really into the history of different electrical parameters, or of electricity, pretty much. So we'll go over a little bit of history of where transformers came about. So, transformers were invented by two Austrian engineers. I'm going to butcher the second guy's name, and I'm probably not going to do very good on the first guy's name either. But it was Otto Belathi and Karoly Zipernowski. So they in partnership discovered how they could build a transformer and step up and down AC voltage and current. So when they found this out, they decided to start making them commercially, and then they became the inventors of the transformer. Years before that, Michael Faraday, who Faraday's law is named after, that was his, that's what he observed. Michael Faraday had discovered the effects of electromagnetism. So he had also kind of figured out, he came up with this law, and then the other two guys later on were able to figure out how to make that law, how to use that law to make something useful. In the coming years, we would have the War of Currents, and that was between Nikola Tesla and Thomas Edison over what type of power should be used to power the world. Because we were coming into a new era. We were in the Industrial Revolution, and so we had discovered steam to power factories and whatever else, and then we had discovered some other thing, and then we had discovered the telephone and all of these other things. But once we figured out about electricity, we figured out how useful electricity could be to power lights and motors and other things. Lights would be the first one to come. And so Thomas Edison had his DC system. And he had a major problem with his DC system because he would be trying to transmit power to an entire city, say New York City. He'd be trying to transfer power to all of New York City. And so he would just try to send the wire, he would just try to send the current and, just try to send power through wires to each home. The problem is that with that fact, we'd be drawing so much power through these transmission lines that they would either become too expensive because they would need to be so big, or they would just melt because they were because they had way too much current. And so this was a big problem because Edison had decided, because Edison, he realized that this was a big problem. So Nikola Tesla came along, and he was working in an Austrian factory, or an Austrian area that happened to be owned, an Austrian company that happened to be owned by Thomas Edison. And once his boss had seen how smart Nikola Tesla was, he shipped him off he said, well, let's send you over to America where you can speak to Edison himself and explain how we can fix our DC system. So he did, and then Thomas Edison promised him $50,000, which was a ton of money back in the 1800s, to make improvements to his DC system and make it function properly. So Tesla worked really hard, and in a few months he had it. He was able to make it work much more efficiently. And then he went to Edison and said, "Hey, where's my $50,000?" And Edison was all, "I was joking. I'm not giving you $50,000. Go do more work." And so Tesla was like, I quit then. So he quit. And Tesla was later able to realize that AC, alternating current, Edison used DC, direct current. Tesla realized that with alternating current, what he could do is he could generate the power. So let's draw a quick drawing. So he could generate the power at a power plant. His first power plant was a hydroelectric power plant. So there you go. I don't know why we ever started using coal and gas, but there you go. It was a hydroelectric power plant at Niagara Falls. So basically we have whatever water sources feeding Niagara Falls, I don't know. But we have that. And then we have what's called a turbine. If you ever been to a hydroelectric power plant, so either the two of the biggest ones in the U.S. are the Hoover Dam and the Grand Coulee Dam. And you can get tours there if you go. The water, the dam blocks the water, and so then the water has to flow through these turbines. And when it's flowing through, it will spin the turbines at a really, really fast speed. And then these turbines are they're basically a motor. So they have magnets and then coils. So we know that rotating magnets will induce a voltage into conductors. So then if we take all these coils, then we can harness this power. So we have the falls, right? Niagara Falls, and so here's our turbine in our power plant. So we have our power coming out of our turbines. Now it's going to be not a terribly high, but not a terribly low voltage. And so we could send this directly off the houses or industrial environments or whatever. But Tesla realized that he would run into the same problem that Edison was having. There would be just too much current being pulled. So instead, he thought, what if we used a transformer and we put in whatever voltage we're getting out, let's say 600 volts. And we step up that voltage extremely high. Like when it's leaving a power plant, we can go as high as 500,000 volts. So, but for the purpose of, if we're going to do short-term, usually short-term transmission lines are about 12 to 14 kilovolts. So 12 to 14,000 volts. So we'll go with 14,000 volts. 14 kV, kilovolts. So after we output that, then what that does is that brings the voltage way high and brings the current way down. Because the more voltage we have, usually the more voltage, the more current. But after you get so high, the current starts dropping. But in low voltage things, usually if you feed more voltage into something, it's going to draw more current, and then you've got a problem in your hands. But in this case, it's the opposite. We reduce the current because it's also a transformer, and that's what transformers do. We can raise, we can, drop down our mains voltage and then bring it back, drop down our mains voltage and then convert it to, I don't know, 12 volts, so then we would take our 12 volts and we would, on the other side of the transformer, we'd have our 12 volts and then we could draw more current with that 12 volts. Anyway, we have our 14 kilovolts. I'll draw some power power poles here. Now we'll draw a house. Actually, we'll draw 2 or 3 houses. Well, let's do 3. Okay. Now, once we've gotten there, then what we can do is we can then use another transformer. This transformer, we put in our, the other thing is, over long distance, wire resistance is going to drop our voltage. So another advantage of having such a high voltage is we'll still have enough voltage when we're ready to get to our source. We'll still have enough voltage when we get to our whatever source we're trying to do. We'll still have enough voltage to the transformer. So then we're going to say that this is 10 kV. So then we drop that down to 120 volts. And there we go. Now we can draw like 400, 500 amps at here. Drop the current to like 2 amps here. So let's say we have like 500 amps here. And then our 10 kV, then we can have like 2 amps here. And then, we have a ton of current here, so we could have like 400 amps here. And there we go. That's how that was a much easier system, a much better system, because we were able to, there was less losses. And also with Edison's system, we would have to have like a substation like on every corner in order to make sure that we would get enough power. So with this, it makes it much easier. Now there are advantages to DC power transmission, and we're starting to move to, especially for long distance right now, like when we're trying to transfer power extremely long distances, like across the country. Then we'll use DC. And then since we have the technology now, we can turn that back into AC. Back then we didn't have the technology to turn it back into AC, but now we do. So we'll use DC because AC we have reactive and active power. That doesn't exist with DC. We just have active power, and there's a lot more good things about DC. It just doesn't work for this type of system. So there you go. That's transformers for you.